Okay, so this is our very first related rate problem, and it involves a sphere increasing at a rate of 2 cubic centimeters per second, and we want to know how fast the radius is increasing when the volume is 10 pi cubic centimeters. Okay, so the main idea is, we have here a balloon, right? So this is a balloon, and let's say I blow in it once. So notice the radius of this balloon right now is pretty much 0. Alright. Okay, now my balloon, I blew in it once, and now my radius got quite a bit bigger. So, you know, let's say, let me grab a ruler real quick. Alright, I've got my handy dandy ruler here. This is Byron Bay, Australia. Okay, so if we measure this, we'll notice that it has a radius of about 6 centimeters. So I just blew in it once and it went from 0 centimeter radius to about 6 centimeters. Okay, now let me blow in it again. So the same amount of air, the volume was exactly the same, but now this time it went from 6 to, if you look at that, that's about, oh, let's just say 9. So this time, instead of increasing again the radius by another 6 centimeters, it just went up to 9. Interesting. So if I try that again, let me zoom out for you. What we get is it went same amount of air again. Now it just went from, let me see here, 9 to, it's hard to see now. Oh, I don't know. Well, it's kind of hard to see now. But anyways, I think you get the idea. Is that every time you put in this, if you put in the same amount of volume, the radius doesn't increase by the same amount each time. So as the volume increases, the rate at which the radius increases starts going down. Okay, and so this is the whole idea behind related rates, is that you have this question that's basically asking you, okay, so if my balloon has a volume of 10 pi cubic centimeters, how fast is the radius increasing? Okay, so to approach this problem, well, we need to, first thing we're going to do is we're going to label everything. Label, and if possible, we're going to draw a picture. Now here our picture is our balloon, and we don't really need to draw a picture of a balloon. I'm actually not that good at drawing, but we'll just let this guy hang out here right next to me. Okay, so let's label our information. Now the first thing is that here we have, it says that the volume of the sphere is increasing at a rate. This is key word. Rates are derivatives. And so the fact that this guy is increasing, the volume is increasing at a rate of 2 cubic centimeters per second, this tells me that the derivative of the volume with respect to time is going to equal 2. So this is my first piece of information. The derivative of the volume with respect to time is equal to 2. This is telling me that the volume is increasing at a rate of 2 cubic centimeters per second. Okay, and then we have the question. It's saying how fast, that means, again, the derivative. How fast is the radius increasing when the volume is 10 pi cubic centimeters. Okay, so since the question is asking me about the radius, well, the rate of the radius, that means I'm looking for the derivative of the radius with respect to time. Okay, so the derivative of the radius with respect to time. This one I don't know, but this is the one that I'm looking for. Okay, and now here, this is really important. Notice that this is a key word right here, when. This tells me when I am trying to figure out the derivative of the radius. Remember, we just talked about with our little demonstration that as this balloon gets bigger, the derivative of the radius with respect to time is going to be changing. Even though we're blowing up the balloon at the same rate, 2 cubic centimeters per second, this guy is constantly changing. So you're always going to have this this value of when, the when value. And this is very important. The when value, which is 10 pi in this case, this is the volume. The when value, you always wait to plug it in the very, very end. Now this might not make sense right now, but later on you'll see if you try to plug this in the beginning of the problem, you'll end up with complete and utter nonsense. So I'm going to write this down. When I write down that I'm looking for the derivative of the radius with respect to time, I'm going to put down right here when I want to know this. I want to know this, the derivative of the radius with respect to time, when the volume is equal to 10 pi. Okay, now that I have all my information down, the second thing I need is a formula that relates my information. Okay, so, well, notice that we have a volume, we're looking for the derivative of the radius, so the obvious choice is the formula for the volume of a sphere. And the volume of a sphere is 4/3 pi r cubed. Okay, once we have the formula, we need to make sure that we have all of this information. So notice that I have a volume. I don't have the radius, but I do know that I'm looking for the radius. And so the next step is going to be to differentiate both sides implicitly with respect to time. Okay. Alright, so what this means is that when so I have my formula here, 4/3 pi r cubed. I'm going to get the derivative of the left and the right side with respect to time. So here the derivative of the left, the derivative of the right, and notice that both these, the volume and the radius, are functions of time, and so when I get the derivative of these guys implicitly, I have to get the derivative of the volume with respect to time. So this is simply derivative of the volume with respect to time is equal to 4/3 pi. That's just a constant, so I'm just going to leave it out of the derivative. And then here, the derivative of the radius cubed. So remember that the radius is a function of time, so that means I have to use the chain rule. So if I use the chain rule here, this is going to be, I bring the 3 down, so 3r squared times the derivative of the radius with respect to time. And you might be wondering, whoa, what's this derivative of radius with respect to time stuff? Well, you have to remember that we just said that the radius is a function of time. So I can write it as r, instead of r, I should write it as r of t, because remember, as you fill up your balloon with air, well, the radius is changing, right? Here, a couple seconds passed and my radius changed. A couple more seconds passed and my radius changed again. So radius is a function of time. So if I have the radius cubed and I want to get the derivative of this, well, I have to use the chain rule, right? I mean, I have to get the derivative of the outside, which is this this whole thing that's being cubed. So I would bring the, let me do it down here so that I have more space. I would bring the 3 down. I would have r of t, and then subtract 1 squared. But then I have to multiply by the derivative of the inside. But now I don't know what the radius function is, but I can write it as the derivative of the radius with respect to time. And so this is nothing more than implicit differentiation, just with different variables. Okay, so once we have that, well, this is the same thing as this one. This one's just written in shorthand, just r squared instead of r of t squared. But that's where the dr over dt comes from. So now once we're looking at this guy, we can take a look at our information and try to see if we have everything we need. So notice that we have this guy, dv over dt, that's just 2. dr over dt, this is the one that we're looking for. We're trying to solve for this one. Now the radius, we don't have a radius, but notice that we're given the volume. We know that the volume is 10 pi. So if we know the volume is 10 pi, well, if you look at the formula here for the volume, if you know the volume at a particular point in time, then you can figure out the radius, right? Okay, so why don't we do that? So we need to find what the radius is when the volume is 10 pi. So we're going to do that right here. So 10 pi is equal to 4/3 pi r cubed. And so if we multiply both sides by 3 over 4 pi, 3 over 4 pi, so what we would get, well, these pi's would cancel, and we would get that r cubed is equal to 15 over 2. And so the radius is equal to the cube root. The cube root of 15 over 2, which is approximately 1.96. And we can grab this guy now and plug it into the radius here. Okay, so then from here it's just a tiny bit more work to plug everything in. We would have, if we plug in this guy, we'd have 2 is equal to 4/3 pi times 3 times 1.96 squared times dr over dt. And if we solve for dr over dt, we should get around 2 over 4 pi times 1.96 squared, which is equal to about approximately 0.04. And this is centimeters per second. And that's it.